have graded your CCNA 3 skills exam, and you can see your grades in Cisco Academy gradebook, so CCNA 3 gradebook. If you have not received the full grade, look it up in the Blackboard. I left you feedback there why you have not received full grade. But overall, I'm pretty satisfied. Most of you did very well on that final skills exam. So, do you have any questions so far with WANs? I forgot to tell you, I have not graded your labs. I'm still working on the labs. So you will receive the lab grade sometime soon. I only graded the final skills exam. So today we will be doing an introduction to frame relay. Frame relay it's covered in chapter 3. So I've been getting some of the guys that are doing it online have actually made a head start and have been trying to do this lab for frame relay. So I'm going to explain sometime by the end of today's lecture. I'm going to explain everything about the lab, but essentially it is going to be difficult to do it on a nice lab. So I would suggest you doing the lab in a packet tracer, and I'm gonna send you an email about this as well. In the Blackboard you can find 2 documents that are going to help you with this frame relay lab. And I'm gonna explain everything sometime by the end of the lecture today. So let's start with frame relay. So for sure you know that frame relay is one of the WAN technologies. So it is a technology used for wide area networks to connect remote LANs. So do you guys remember maybe from chapter 1 or chapter 2 what type of WAN technology frame relay is frame relay? So options are a lead line, circuit switched, packet switched, public. So what do you remember? What do you think? What type of WAN technology frame relay is frame relay? It is? What? Packet switch. Very good. It is a packet switch. And let's see. Do you guys remember what are the layers on which WANs work? Layer 1 and layer 2, very good. So don't ever forget that. So frame relay uses virtual circuits. It could be switched or permanent virtual circuits to connect remote locations. The frame relay provider can be public or private, and you will ask for a frame relay provider to create a virtual circuit for you with certain properties, and you will be requesting a certain amount of bandwidth, and I will tell you a little bit later how that bandwidth is called. Now, again, to remind you, in CCNA, we are looking at the network from the customer perspective. So which means that we do not care what kind of technology the provider has inside, and we do not need to know how provider decided to implement that frame relay inside of their network, as long as they are giving you that virtual circuit, frame relay virtual circuit, that connects your two remote locations with certain bandwidth. So in the lab, we will simulate that frame relay provider. We call it the frame relay cloud. And you'll be using a certain device that's already been pre-configured that's going to simulate that frame relay provider. In the lab instructions, they are telling you that they're giving you a configuration that you can use and apply to the Cisco router and convert Cisco router into frame relay switch. Excuse me. Now, you don't need to know that configuration. So that configuration is there just to help you, and you can copy and paste it. And again, that's just one way to implement frame relay. And it is kind of expensive if you use a Cisco router for frame relay switching purposes. And again, as I said, you really don't need to know how that is implemented inside of the service provider, as long as you are getting that service, as long as you're getting the service you signed up for. So as I mentioned earlier, the foundation of the frame relay technology are the virtual circuits. And the virtual circuits carry packets from one router, from one remote location to another remote location. And the virtual circuits can be permanent or switched virtual circuits. More common are permanent virtual circuits. Now, can I ask you this? What do you think is, where is DCE and where is DTE on this picture here?
Side of the closed side, and DTE side of the local side.
Right, so DTE would be your router, right? That you are using to connect to the frame relay network. And DCE, example of DCE, would be that device you are connecting to, and that's a frame relay switch. Okay, so frame relay switch in this example will provide the clock for this link. So the virtual circuits are identified by what we call DLCI, Data Link Connection Identifier. So DLCI, or DELCI, is layer 2 address of the frame relay virtual circuit. So that's a layer 2 address of the frame relay virtual circuit. So that would be equivalent of MAC address on Ethernet, right? So on frame relay, we don't have MAC addresses. We are using DLCIs that identify that virtual circuit. Now, let's look at the bottom picture in the corner. So we have router 1, 2, and 3, which is not labeled, but we have router 3. And 4. It's labeled 6 here. Yeah, sure. How intuitive. Anyway, let's say you would like to connect your router 1 to router 2. So you would like to connect remote location 1 and remote location 2. So you will connect them by asking a service provider to create a virtual circuit between those 2 remote locations. Now, what if you want to connect, in addition to that, you want to connect router 1 to router 3. And this is my router 3 in the corner here. So service provider will create another virtual circuit that goes from router 1 to router 3. So look at this access link from router 1 to the frame relay network. So this access link from router 1 to frame relay network is actually carrying 2 virtual circuits. So over that single physical access link, you have 2 virtual circuits. And each one of those virtual circuits is identified by DELCI. So frame relay, again, works on layer 1 and layer 2. So it means that frame relay creates a data link layer encapsulation. And it begins with a flag, ends with a flag, it has address, it carries data, and it also has a frame check sequence. So it is kind of similar to the, say, Ethernet encapsulation. Now, the address here for frame relay would be what? DELCI number, right? Now, how do you find out, how does your router know how many virtual circuits have been created on that access link? And what is the status of those virtual circuits are they active? And what is the Delphi number of those virtual circuits? So frame relay uses a protocol called LMI, Local Management Interface, that is exchanging messages between that frame relay switch and your router, so that a router can learn about how many virtual circuits have been created on that link or on that access link. What is the status of those virtual circuits? And what is the Delphi number of the virtual circuits? So what people commonly where people commonly make a mistake is that they forget that LMI protocol works only on that access link between the router and the frame relay switch. The frame relay protocol, which is used, and the frame relay encapsulation is used to encapsulate traffic that you send from, say, router 1 to router 2. Let's say this is router 2. So when you send traffic from one remote location to another remote location across that virtual circuit, that traffic is going to be encapsulated inside of the frame relay frame. Now, how do you know what is the Delphi number you need to use to reach certain mixed hop IP address? That's one question. Now, let me draw a topology here that's going to illustrate that. So let's say we have three remote locations that use router 1, 2, and 3 to connect to the frame relay network. So let's say this is router 1, router 2, and router 3. So behind each one of those routers is a LAN. Okay, that could be a large LAN. I'm just simplifying it. Now you would like to connect those three locations. So let's say a local network behind router 1 represents headquarters, and this is just remote site 2, and this is remote site 3. So you would like to create connection from remote site 2 and from remote site 3 to the headquarters. And you looked into all the options and decided that frame relay is going to be the WAN technology that you are going to utilize. So you ask a frame relay service provider to create that connection. Now, they are going to create a virtual circuits between those to connect your remote site to the headquarters. But you need to connect to the frame relay network. How do you connect to the frame relay network? Well, you connect using serial interface and a serial link to the frame relay switch. So this is your access link. From serial interface to the frame relay network. Okay? Now, those virtual circuits that I labeled in red have identifiers, DELCs, right? So I'm going to write down that the virtual circuit that goes from router 1 to router 3 has DELC number 103. And the virtual circuit that goes from router 1 to router 2 has DELC number 102. Now, DELC numbers are only unique on the access link. So on this access link, DELC numbers have to be unique. What does it mean? It means that on the other end of this virtual circuit here, on the access link from router 2 to the frame relay cloud, DELC number doesn't have to be 102. It can be, say, 201. Okay? On the access link from R3 to frame relay cloud, DELC number can be, say, 201. What's that?
201 or
301. 301. Oh my god, I'm dyslexic. I'm writing down the 301 and I'm saying 201. So 301, right? Now, how do you know you need to send, say, if you're trying to reach from LAN 2, so if you're trying to reach from here, from LAN 1, if you're trying to reach LAN 2, how do you know which one of the virtual circuits you need to use? So let me add one more layer to this, and that's going to be IP addressing. So let's say that On WAN 1, we are using following IPs. Let's say the network behind the headquarters is really big. On LAN 2, let's say we are using 10.2.0.0. And let's say here we are using 10.3.0.0/16. Now what about the network that connects those remote locations? Let's say that for the virtual circuits and for that network we are using 10.10.0.0. So we are being really wasteful here. But let's say IP on this interface, on the serial interface on the router 1 is going to be 10.10.0.1. IP address on router 3 is going to be 10.10.0.3. And IP address on router 2 is going to be 10.10.0.2. Alright? So let's say that we are sitting here and we need to send some traffic to LAN 2. How do we know that we're going to use Del C 102 versus Del C 103 to reach that LAN 2? So do you guys recall what is the protocol that connects layer 2 and layer 3 addressing on Ethernet? Was that? Yeah, the protocol. On Ethernet. IP, no, that connects layer 2 and layer 3 addressing. It starts with A. A protocol.
802. You said 8?
Not 8. A.
As an apple.
As an apple, that's correct.
Apple. Apple.
Apple. Apple talk. No.
Oh, harp. Yeah.
Harp. Huh?
Cool, got it.
So ARP, how does ARP work? So you know the IP address, right? But then you would like to find out what is the MAC address, so you send an ARP request. Now DELCs, I told you, are like layer 2 address, right? MAC is layer 2 address, right? So DELCs are layer 2 address. And here the question is, what DELC number you need to use to get to the certain IP address. So what do you think the protocol would be for that? The protocol that would map that? DELC to an IP? How about ARP? Hey! So, on frame relay, it works slightly different. You will not be, so when you have traffic from one remote location to another remote location, you will not be sending ARP. Rather, before you can send any traffic, but after the virtual circuits have been established, inverse ARP mechanism is going to be triggered, and let's say a router 1 is going to send through the virtual circuit with Delphi number 102 inverse ARP. Inverse ARP message is going to travel through this virtual circuit, and that inverse ARP message is going to say my source IP address is 10.10.0.1. So that's my source IP address. And as that inverse ARP message travels through this virtual circuit, it ends up at router 2. So router 2 logs that inverse ARP message that has source IP address 10.10.0.1. I don't know if you can see that. Oh yeah, you can. And it logs that inverse ARP message was received through a virtual circuit with Delphi number 201. Okay. Now, router 1 is going to do the same thing. It's going to send inverse ARP message with the source IP address 10.10.0.1 through the second virtual circuit, and that virtual circuit ends up at router 3, right? So router 3 is going to log that inverse ARP message with a source IP address 10.10.0.1, and it's going to say, oh, I received that inverse ARP message through the virtual circuit with Delphi number 301.
Question, I might have missed this. So where is the 1010 network?
So 1010 network is here in the cloud. So this is 10.10.0.2, this is 10.10.0.3, and this is 10.10.0.1. Okay, on the interfaces, on the serial interfaces that connect to the frame relay network. All right. Now, router 2 is going to do the same thing. As soon as you configure frame relay and the router 2 learns the virtual circuit and Delphi number, router 2 is going to send inverse ARP message through this virtual circuit, and it will end up at router 1. So router 1 is going to log the source IP of that inverse ARP message was 10.10.0.2, and I received that inverse ARP message through Delphi 102. Okay? Router 3 is going to do the same thing. And when router 1 receives that inverse ARP message, it's going to say, oh, the source of that inverse ARP message was 10.10.03, and I received that inverse ARP message through Delphi 103. Does it make sense so far? Now, at this point, when router 1 tries to send traffic to router 2, it is going to look up this inverse ARP table, or table that has been built by inverse ARP, and it's going to decide that it needs to use virtual circuit with Delphi number 102, because that's the virtual circuit that will lead to router 2 IP address 10.10.02.
So are we talking a routing table here?
So this is like MAC addressing table, right? MAC addressing table, or MAC address table, rather the ARP table. So ARP table on the Ethernet connects or associates MAC addresses and IP addresses. So inverse ARP table associates on frame relay, associates IP addresses and Delphis.
So on the router itself, this is where that table resides?
Right, yeah. Now, this is just the first step. And at this point, so after that, router 1, 2, and 3 will be able to reach each other. Now let me ask you this. Do you think that, let's say I have a device on LAN 1 here. I have a PC that resides here on LAN 1. And I have PC that resides here on LAN 2. So do you guys think that after inverse ARP table has been built, a PC on LAN 1 will be able to reach PC on LAN 2? What's that? Yeah, both sides have frame relay encapsulation, and inverse ARP table has been built. What's that? Good point. So the inverse ARP table tells you only how to reach connected neighbor, right? But it doesn't tell you how to reach beyond that. So you still need a routing protocol. So after the inverse ARP has built that table and you know what Delphis you are going to use to reach certain next hop, you still need to configure routing protocol. Okay? No, LAN, right, LAN to LAN. They're not in the same network. right? LAN 1 is 10.100/16, and LAN 2 is 10.200/16. Okay, I will have a demonstration using Packet Tracer. So the frame relay configuration is actually very simple. One command, only one command is needed for the frame relay, and that is encapsulation frame relay on the serial interface that connects to that, for that access link that connects to that frame relay network. So under the serial interface, you'll simply type encapsulation frame relay, and that's all. Now you can make it a bit more complicated. So the inverse arc does work by default. You don't have to configure it. It will work. But you can choose to disable inverse arc and create that map between Delphi and the next hop IP address yourself. If you decided to do that, the command is going to be frame relay map IP address, and then the next hop IP address, and then a Delphi number that you are going to use to reach that frame relay link. Now, frame relay is also known as NBMA network. What is NBMA network? NBMA stands for Non-Broadcast Multi-Access Network. Non-broadcast because it doesn't support broadcast. Now, routing updates, I think they're sent by broadcast. Well, some of the routing updates are sent by broadcast, right? Some of them are sent by multicast. Well, frame relay has issues with multicast as well. So let's go back to let me draw a new topology. So again, my 3-router network. And again, let's say R1 is a headquarters, so you want to connect remote site 2 and remote site 3 to the headquarters, and you ask the service provider to create a virtual circuit between those two remote locations. And here is one virtual circuit, and here is another virtual circuit. So let's say you enabled OSPF or EIGRP, so it doesn't matter, some routing protocol. You enabled some routing protocol, or let's even better, let's assume we created a static route. So the virtual circuits tell you that traffic from router 2 to router 3 can only go through the virtual circuit, and which means traffic from router 2 to router 3 is going to go through router 1. Okay, that's the path of the traffic. Now, in order to learn the routes, you need to enable routing protocol, and routing protocol sends updates either by broadcast or by multicast. And non-broadcast multi-access network does not support broadcast. That means that broadcasts don't work in a way you learned on Ethernet. So on Ethernet, you just send one broadcast frame, and all devices connected to that common network will receive that broadcast, right? And the key is here, you send one frame, one broadcast frame, and all devices are going to receive that. Now, for frame relay or non-broadcast multi-access networks, you need a special configuration of routing protocol that will tell the routing protocol that it needs to create one update, which is sent by broadcast or by multicast, and send it through this link, but it also needs to create a duplicate copy of that update and send it through another virtual circuit. So you cannot send one frame, one broadcast frame, and expect that everybody will receive it. Rather, you need to send one frame through each one of the virtual circuits. Now, there's one more issue, right? There is one more issue with a routing protocol configuration, is that, let's say you enabled RIP routing protocol, and RIP routing protocol is sending an update from, let's say, router 2. So you're sending an update from router 2. That update hits router 1. Now, router 1 should be sending that update to router 3, so that router 3 learns about this network here behind router 2. But router 1 doesn't do that. It doesn't send that update to router 3. Why not? Anyone remembers? What's that? It starts with this. If something rule. If the, what's that? No. Standing is Split Horizon. He learned it yesterday, so it doesn't count. Split Horizon rule. Right? What does Split Horizon rule tell you? So you're not going to send updates through the same interface to which you learned them, right? And if you look at the router 1 learned that update through serial 0 interface. So this is serial interface, and therefore it should not be sending that update through the same interface out, right? So you can see how frame relay has issues with routing protocols. First of all, the broadcast, and secondly, Split Horizon rule. If you let Split Horizon rule on, well, that update from router 2 is never going to reach router 3. So router 3 is never going to learn about the route behind the network, behind router 2.
Can you just give us a quick review of Split Horizon? Now, is that something that's part of the protocols, or was it a feature of the router?
Part of the protocol, part of the
like RIP, OS,
RIP. Part of the RIP, right, part of the RIP and EIGRP protocols.
That was just a feature
of the protocol, yeah. It's a feature of the protocol. It's used and is one of the methods that tries to prevent loops.
Like the routing.
Routing loops, right. Okay. So the routing protocol configuration over EIGRP is covered, so especially OSPF is covered extensively on the in CCNP. Now, at the beginning, I told you that you will ask a service provider to create a virtual circuit with a certain bandwidth. Now, the bandwidth that frame relay is using is called committed information rate, CIR. So committed information rate is a guaranteed amount of bandwidth. Let's say you're connecting two remote locations through the frame relay network. And you ask service provider to create the virtual circuit, and the bandwidth essentially with a certain service level characteristics. So one of the numbers from the service level agreement is committed information rate. So committed information rate is the guaranteed amount of bandwidth. And the committed information rate is measured as amount of data in bits, right, that you can spend over certain time, and that time is called committed time. So this becomes your committed information rate. Now, since this frame relay network is packet switched, right, you're sharing that frame relay network with other customers of this service provider, right? And if the frame relay network is not heavily utilized, you can get more bandwidth than just committed information rate. You can get through this measured also through the committed time. You can send on top of this data, you can send which is called excess, I'm going to label it as EC, and EC is excess burst size. So when you add that up, we can get a higher, or you can get more bandwidth. And that's called excess information rate. So you can send more traffic over that virtual circuit from R1 to R2 if the frame relay network is not congested. But what's the catch? The catch is that this data that you are, the excess burst size, that you are sending on top of the committed burst size is going to be flagged. That's the frames that belong to that excess information rate are going to be flagged And the flag is in here. The flag is DE flag. DE flag stands for eligible to be discarded. So if the frame relay network experiences congestion, devices inside of the frame relay network are going to start dropping the frames that have that flag, that have DE flag. Now they're not going to drop the frames just like that. They're going to send a notification to router 1 and router 2 saying, well, slow down. The network is experiencing congestion and you should slow down to the committed information rate. Because the committed information rate is guaranteed amount of bandwidth. So at any given time, you will be getting at least that bandwidth.
Flow control or something that's managed?
Yes. So that is called flow control. So frames, again, that are above that committed information rate have the DE flag. So DE is a field that says eligible to be discarded. If the frame relay switches detects congestion, they're going to start dropping those frames. But they will also send information or notification to sender and receiver to slow down, and that notification is called forward explicit congestion notification and backward explicit congestion notification. That's also a flag in a frame relay frame that's going to be sent to the source and destination, telling them, well, slow down and drop the speed to the committed, to the guaranteed, to the minimum guaranteed speed, which is called a committed information rate. Does that make sense? So that's how you can get more bandwidth, and that's the information you're going to agree in a service level agreement. You're going to agree what is the guaranteed amount of bandwidth, and you're going to agree on what is the excess burst size, how much more data you can push through the frame relay network, but you're risking it that those frames might get dropped if the service provider experiences congestion in their network, because their network is shared with other customers. Okay? Now, any questions?
Digital synchronous transmission?
It is a synchronous. Oh, sorry.
Digital?
It is digital. It is synchronous because you still need. This is a serial link. The access link is a serial link between DC and DT, and you still need a clock, right? Now, there is link between the speed of the access link and committed information rate. So I'm making it even more complicated. So let's say we have a third router and from router 1 we have a virtual circuit that connects router 1 and router 3. Now let's say the committed information rate for this virtual circuit that connects router 1 and router 2 is 64 kilobits per second. And committed information rate between router 1 and router 3 is, let's say, 128 kilobits per second. So you have this access link that connects you to the frame relay cloud, frame relay network. And the CIRs are just speeds of the virtual circuits. And you have two virtual circuits on this access link. So what do you think? What should be the speed of the access link? Minimum should be, so this access link needs to support two virtual circuits and speed 64 and 128. So what should be the speed of the access link? Very good, yeah, it should be at least 192 kilobits per second in order to support those virtual circuits. Okay. So the access link, the speed of the access link matters. So you need to know what should be the speed of the access link. So the speed of the virtual circuits is essentially limited by the speed of the access link. Okay? And the access link speed can be T1, T3, or something, or fractional T1, something really low, like 100. In this example, it should be a minimum 192.
Multiples of 64.
Right, so fractional T1 is multiples of these zeros, yeah. Okay. Any questions? Yeah, it's time for a break. So let's take a break. Let's take 15. And then after a break, I will show you frame relay configuration, and we'll be doing that in a packet tracer. All right? So I'm going to stop recording. And we'll continue recording after the break.
Oh, yeah. I don't know if the lab is back on here. You can do it.
Okay, so I'm going to start recording. And I was hoping that we'll do some packet tracer activity that we can practice the frame relay configuration. So can you guys download let's see. Oh, no. I don't think that's it. So I'm just trying to log into Cisco Academy, and I can share my desktop with you guys. So I would like you to download certain packet tracer file from chapter 3 that we can use to practice, and now my computer will crash. That we can use to practice frame relay configuration. No. Let me try through the Chrome. Oh, and I promised to explain about that frame relay lab. So I would, because I heard a lot of people having issues with the frame relay lab on the CNET lab, I would recommend you doing that lab in a packet tracer actually. So how would you do that lab in a packet tracer? Now you would, on a blackboard, let me show you, you would use a file that I posted there, the blank frame relay packet tracer file, and this frame relay lab is the document that describes instructions how to use this blank frame relay packet tracer file. So this packet tracer file, let me download it and open it up actually, contains a cloud to which you will be connecting to. Actually, I can use this this packet tracer file to show you. So you're going to be connecting using DCE. So DCE serial 0 to router 0, DCE serial 1 on the frame relay cloud to serial on router 1. DCE again serial 2 on a cloud to router 2. Okay? And this cloud has already been pre-configured for your lab. You don't have to do anything, any configuration on the cloud, and you don't need to know the configuration of the frame relay switch. But here is another, so that's if you want to do it in packet tracer. Now, if you decide to do the lab on the actual equipment here, you will need to use one of the routers and configure it as a frame relay switch. And that configuration is part of the lab. So you don't need to remember and you don't need to understand that configuration. You just take that configuration and copy and paste it to the router. Okay? That's all. You don't need to understand it. You don't need to remember it. You don't need to know it. But easiest thing you can do is you can use this, you can do the lab in a packet tracer, and you can use this blank frame relay cloud for the lab I've assigned you. Okay? Now to our...
So we should not use NetLab for chapter 3?
Yeah, you will run into issues, and it would be easier to do it in a packet tracer. Okay, let's download a packet tracer file on a page 322/2. So can you download that packet tracer file? So have you downloaded the packet tracer file?
I'm trouble opening.
All right, so can we start? So we will start with basic frame relay configuration. So as I said, the frame relay configuration only requires one command, and that is an encapsulation frame relay on that serial interface. So let's type that command on all of the serial interfaces on router 1, on the serial interfaces connected to the frame relay network on router 1, 2, and 3. So let's do that. And the serial interfaces, I believe all of them are serial 00. Yeah. So all of them are serial 00. And you don't need to configure a clock on that interface because your side is DTE. So this is the command, and that's all. No shutdown.
Which line was it?
322/2. So have you enabled frame relay encapsulation on all three interfaces? On router 1 on all three routers. So you should have a green light, right? Now, how do we know that frame relay is working? Well, there are some commands that we'll be using to make sure that the frame relay is working. So, first command is show frame relay PVC. So PVC stands for permanent virtual circuit. Okay? So, what does that mean? The output of show frame relay PVC. What does it mean? To show frame relay PVC. You need to enable with an OM3, so on router 2 and make an installation. You need to do an OM3 router. And interface 000. So this output tells you that on the serial interface, you have two virtual circuits. Right? Two virtual circuits are connected to your serial interface. And it tells you the status of those virtual circuits. They're active, both. Both of my virtual circuits on this access link are active. And one virtual circuit is 102 and the other one is 103. Okay? You can do that command on router 2 and router 3. So show frame relay PVC. Now, the next step, next command you would use is show frame relay map. Now this map, oops, show frame relay map, let's see. No map. Let's see what has been configured. I know. So frame relay, the output of show frame relay map will show you that map between the del C and the IP address. But let me see why it's not showing up. Oh, I can, it's locked, device is locked. Unfortunately, you will not be able to see the result of inverse arc in this lab. So we will need to configure map manually. So we will need to manually configure the map between the del C and the next hop IP address. So they are telling us in the instructions, they are telling us that on R1 you're using Delphi 102 to reach router 2. And router 2 IP address is 10.1.1.2. So we'll need to create a static map. Instead of inverse arc, we'll need to create a static map between the Delphi number and the next hop IP address. So we're going to say frame relay map IP. So on router 1, frame relay map IP, and we are going to map the router 2 IP address with the local Delphi 102. So Delphi 102 is on router 1. And that's the Delphi, that's the number of virtual circuit that's going to get you to the router 2. So virtual circuit with Delphi number 103 is the virtual circuit on router 1 that's going to get you to router 3. And broadcast at the end is required.
Can you explain a little bit about why that's required?
The broadcast keyword? It's required to support broadcast updates. So it's telling essentially the...
So normally it's not accepting broadcast.
Normally it's not going to know what to do with a broadcast frame. So in this case, when you say broadcast keyword at the end, it's going to create a duplicate broadcast frame and send it through each one of those virtual circuits. So let's do this. Frame relay map on router 1. So global configuration mode, frame relay map, and we are mapping again the IP address of router 2. And through this map, we are telling router 1, if you want to reach 10.1.1.2, use this virtual circuit. Oh, that's the under interface should be configured. What am I saying? That's the interface command. And then we'll do another frame relay map that's gonna help us reach router 3, because we are mapping router 3 IP address with our 103 virtual circuit. Now we need to do the similar configuration on router 2 and router 3. So I'm going to open a notepad and I'm going to write it down what you need to have on router 2. So can you guys help me out? How is my frame relay map going to look like on router 2? So what am I trying to reach on router 2? I'm trying to reach router 3 and router 1, right? What's going to be IP address of, what's the IP address of router 1? Right, 1. It's 10.1.1.1. And then, according to the instructions, Delphi 201 on router 2. So again, this is the output of show frame relay frame relay PVC. So the router 2 has a virtual circuit with delta number 201 and 203. So according to instructions, 201 will be used to reach router 1, and 203 is going to be used to reach router 3. So in my notepad, I'm going to have a frame relay map 10111, and then delta number 201, and then broadcast keyword at the end.
If you want to wipe out, you can just put a no in front.
Sure, yeah, of course. And then second frame relay map is going to be to reach router 3. Are you guys able to follow? Any questions? So this is the configuration you need to have on router 2. Alright, who needs help?
Instead of 102, 103, 201, 203, is that alternately or do you just get assigned?
That's assigned.
So by the service form.
Right, so service provider tells you 201, so you can see this. show frame PVC. That's what you can see. You have two virtual circuits. One has the number 102 and the other one has 103. And the provider needs to tell you, where does 102 go? Where does 103 go?
So this is the free configuration of it.
They will tell you. Now, if you have typed that in, then verify it using show frame relay map command. So this is the result of your input. Now this could have also been created dynamically. You didn't have to type in the frame relay map, but on this lab it doesn't work, unfortunately. But this map could have been created by protocol called inverse arc, right? Inverse arc. Now, unfortunately for this lab, inverse arc doesn't work, but by default, the inverse arc will be working. You don't have to configure anything. For this lab, it's not working. Now, this tells you it is static configuration, right? If it was learned through through inverse arc, it would tell you dynamic map. So this map tells you if you want to reach 10.1.1.2 next hop IP address, we'll use send traffic through Delphi 102. Send traffic through virtual circuit 102. If you want to reach 10.1.1.3 IP, send traffic through virtual circuit 103. So at this point, try to verify the map on router 2 and router 3. So let's do that quickly. I have map on router 2 and I have a map on router 3. So let's see if it's working. How do we verify that it's working? Let's ping, right? Let's ping from router 1 to router 2. No. At this point, ping unfortunately is still not gonna work. Oh, that's why the inverse arc wasn't working. Now, they're telling you that LMI protocol that is used on that access link between DCE and DT, between the router and the frame relay switch, there are 3 versions of that LMI protocol, and using command show frame relay LMI, I noticed that the LMI type that my routers are using is syscall, And in the instructions here, they're telling me that LMI type is NSI. So the LMI, again, is a protocol that works between the router, your router, and the service provider frame relay switch. And through LMI protocol, you're learning the status of your virtual circuit, the number, Delphi number of your virtual circuit, and what else? That's about it. So in this, the LMI protocol has 3 different variations, or 3 different types. So it can be Cisco, the NSI, and what is the third one? I forgot what is the third one. Anyway, by looking at the output of show frame relay LMI, I'm seeing that messages are being sent, LMI messages are being sent and received. But they're also telling me the LMI type that frame relay switches are using is NSI, and my router is using a default LMI type, which is Cisco. So I would need to change it to NSI. So how do I do that? It's one simple command on the interface that connects to that frame relay network. So my serial interface, I type frame relay LMI type NSI. And I need to do that on all 3 routers. So you notice one thing after I type my LMI type and change it to NSI, that the interface, serial interface, the protocol changed state to up. So now my interfaces are working. So my serial interfaces, serial 00 interfaces are working. And let's try pinging now. See? So now ping between router 1 and router 2, and say router 1 and router 3, and router 2 and router 3 is successful. Right?
Okay, so could you just recap what changed that made things successful?
So
LMI.
LMI protocol, it works between DC and DT, between your router and the frame relay switch. Has 3 different types. On the frame relay switch, LMI type was NSI, and LMI type on the Cisco router was Cisco. So they were not the same, and they were not understanding each other. And that's why the interface was not the line protocol, so the layer 2 on the serial interface was not working. And as soon as I changed on the router LMI type to MSI, which is now identical to LMI type on the frame relay switch, it started working. All right.
And just another question. We've talked about this before. I keep forgetting. But just taking R1 to the cloud, the DCE and the DTE on the R1 side, on the customer side, is that
No, that's DTE.
DTE?
So cloud, frame relay cloud is providing the clock.
Okay.
So the DCE side is on the provider side always.
Is that different from what we've seen before?
It's different from the lab. You know, in the lab we simulate a WAN link using that back-to-back, and we have to have a DCE somewhere to provide a clock for that link. So that's why we configure the clock on the router, which you will never see in the real world.
More real.
Yeah. So have you guys changed the frame relay LMI type?
Yeah, it works.
Okay. Now, let me ask you this. Do you think, and have you tried to ping from router 1 to router 2? Okay, so ping works, right? Now let me ask you this. Do you think that ping from, say, PC1 to PC3, would that work or not?
Yeah.
Oh. Huh. I wasn't expecting that. Why not? They already have routing protocol configured. Okay? They have routing protocol, so I didn't expect that they will have routing protocol configured.
Yep.
Mm-hmm. So it is working because I didn't expect that there will be routing protocol. So it is working because routing protocol is configured. If we didn't have routing protocol, where we wouldn't be able to ping from PC1 to PC3, right?
So the routing protocol is able, all three routers are getting the same updates?
Mm-hmm. Now, routing protocol would not work if the frame relay network is not working, right? Because frame relay network is on the layer 2 and routing protocol is on layer 3. So if your layer 2 is not working, well, of course that routing protocol is not going to work either. So before you start troubleshooting a routing protocol in a frame relay network, make sure that the frame relay network is working. So commands that I show you that you can use to verify and troubleshoot frame relay are show frame relay PVC, show frame relay map, and show frame relay LMI. Now, I want to try something out because I think that was the reason that inverse ARP was not working in the first place. I'm going to be removing the maps. Huh. What did I do? I removed all the frame relay maps. Right? I don't have any more maps. And I do show frame relay map. I do see it is dynamic. So what does it mean exactly? It has been created dynamically by these burst start. So why wasn't it working at the beginning in the first place? Because LMI type was wrong. So the router was not talking to that frame relay switch. They couldn't quite understand each other, and that's why burst arc wasn't working. So let me show you what configuration I have now on my router on the serial interface. Two commands. Encapsulation frame relay. Of course I have IP address, right? But I have encapsulation frame relay and frame relay LMI type and the time. That's all. The map has been created dynamically by burst arc.
When you go back to the map, it shows the street though.
Does it? Oh yeah, that's about it.
That would have shown
in the side, yeah. Very good catch. So the default LMI type on Cisco router is of course Cisco, right? If the frame relay switches on the provider side happen to use that LMI type, I wouldn't even need this command, right? I would only use encapsulation frame relay command.
So question, just to, so I can kind of understand the basis. So we've got 3 routers and we're going to use frame relay.
Right.
There's serial interfaces making the connection into the cloud.
Right. So serial interfaces are just access links. So you use that for the access link to the frame relay network.
Are they the same serial interfaces that we use for TCP or?
Yes. Yeah.
So there's nothing, now on these particular routers, are they frame, do they have any frame relay software? They specially?
No, it's your serial interface. Same serial interface that you use to connect to the frame relay switch. The only thing you need is encapsulation frame relay. Before it was encapsulation TTP or encapsulation HDLC. Now it's encapsulation frame relay. Okay. All right, so let me review. So frame relay is a packet switch technology. It's a WAN technology, which means it describes layer 1 and layer 2. The frame relay is using LMI protocol between DC and DT, between Cisco router, a DTE, and the frame relay switch, a DC, to discover virtual circuit, the status of the virtual circuit, and delta number of the virtual circuit, and to keep alive that virtual circuit. So frame relay service will create virtual circuits between those remote locations you're trying to connect through WAN. The type of the virtual circuit, the most common type of the virtual circuit is permanent virtual circuit. And the virtual circuit is going to have a guaranteed amount of bandwidth. A guaranteed amount of bandwidth is called committed information rate. So that's one of the parameters you will agree upon with the service provider of that frame relay virtual circuit. Another parameter is the amount of data you can send on top of that guaranteed bandwidth, which is called excess burst size. But the catch is that that data on top of the committed, on top of the guaranteed amount of bandwidth you are sending is going to be flagged. It's going to be flagged with a special flag that's called DE flag, eligible to be discarded. Because in the event of the congestion of that service provider frame relay network, the frame relay switches are going to start dropping those frames that have a DE flag. Now, they're not going to drop those frames just like that. They're going to drop the frame and they're going to notify the sender and receiver to slow down to the speed, to the guaranteed speed. So that's called a flow control, and flow control is provided through those forward and backward explicit congestion notification frames. The access link through which you are connecting to that frame relay network can carry multiple virtual circuits. Now, the speed of the access link has to be at least the combined guaranteed speed of those virtual circuits that you have on that access link. Frame relay, the Frame relay is known as a non-broadcast multi-access network, NBMA. And non-broadcast multi-access networks have issues with broadcasts and split horizon rule of RIP and EHRP routing protocols. So routing protocol configuration needs to be adjusted to work over NVMe. And that discussion is for CCNP level. Right? And you don't know how lucky you are. It's really, it can drive you crazy how many different combinations it has. Now, I would say this is one of the most difficult chapters in CCNA 4, and a lot of people don't like the frame relay. I have not covered, and I'm not planning to do that today. I'm going to do that next time. The frame relay configuration on sub-interfaces. I think if I do that, you're going to get just a headache, and you will end up with a frame relay nightmare. So I'm going to let you digest this information, and we'll finish with frame relay configuration on sub-interfaces. We'll leave that discussion for the next time.
Now, is this an old technology? I might have answered this last week.
It is kind of on the older side.
What's replacing this?
I guess MPLS. So MPLS could be one of the technologies that's replacing it. It's still used. It's still used widely. It's not like there's some.
We need to know this.
Yeah.
We might not like it.
Right. It is still widely used. Yeah.
There's a learning college music.
To be honest, I don't know what type of WAN links they have. Yeah. I'm not going to say it. All right. Any questions? All right, so I'm going to stop recording. And we will wrap up